So, hi, welcome to Module 1, Classification of Goods and Types of Systems. This presentation's by Springtech Consultancy and Design, who will basically design systems, consult on systems, and actually do a bit of training. Myself is Alan Crichton. I have 23 years experience in the industry. Started off as a designer and moved my way up to a project manager, then on to operations manager, operations director, and then finally a director. At present, I own and run Springtech, and if you're looking for any information, you can get it on the website www.springtech.co.uk. On that, you'll find out about the courses that we do, course dates, policies, and all the other services that we carry out. So, this presentation benefits from 3 hours CPD. If you like to get a CPD certificate with the hours attached to it, if you don't mind, just send me an email at ac@springtech.co.uk. Hold up for a second if you want to take notes. Right, so we'll get started. So, why do we install sprinkler systems? We install sprinkler systems to protect property. In doing that, we protect the premises, we protect the stock, we protect the plant, machinery, all from the effects of fire. Okay, so that would ensure business continuity and business would keep running, etc., etc. Also protect schools, make sure that they keep operating and they can offer education to children, etc. The other reason to do it is to protect people and maintain a safe means of escape from the building. Now, life safety systems generally come in when you can't achieve the 45 metres escape route from any part of the building, and you may find that building control officers ask for life safety systems in that instance. That's something that the fire engineer at the start of the contract would look at and determine whether it was a life safety system or not. So, I'm going to run through a couple of scenarios here. Cameron House Hotel is a luxury resort on the banks of Loch Lomond. The hotel complex comprised of 44 acres of land around the hotel and the Cameron Club, and it was formerly the Carrick Estate. Situated 2 miles north of the hotel has 2 golf courses, spa, etc. On December 18th, 2017, a fire ripped through the old part of the building, and the recent reports suggest that a porter had put hot ashes in a cupboard, and that's what started the fire. But the fire actually burned for 24 hours, with 14 fire engines being dispatched to extinguish the fire. Okay, the fire investigation report has been issued, as I said, and people have been prosecuted for that. But over 200 people were evacuated from the hotel, and 2 people from London died in the effects of fire. Yeah, 3 other people had injuries from the fire, and that was the result. So basically, what you've got is the old part of the building in the centre, which was destroyed totally, and to the left was the leisure complex, which was relatively untouched. And then you had the bedroom block to the back of it, again, relatively untouched. Okay. Now, the hotel's gone through a major refurb. I don't think it's finished yet. It'll still be ongoing. But they're actually installing a water mist system into the hotel at the moment. While they're doing that, they're upgrading the leisure part and extending the hotel quite significantly. So, just a quick discussion on how sprinklers work and timescales and whatnot. When you get a fire, in a minute and a half, you tend to get the smoke set off the fire alarms, and that obviously indicates the fire, so that maybe wake people up and whatnot, get them out. And in that same period, the sprinklers, if you have them, will activate. And when they activate, they control the fire until the fire brigade get there and they'll extinguish it. Now that could be contained to one room or one area. So when it comes to business continuity, you can basically clean that one room, shut that one room off and keep the rest of the hotel, the rest of the care premises, the rest of the school active. So it's not actually affecting the continuity of the business or the operation of the site, etc. But that's the reason to have sprinklers. Control fire. If you've only got a smoke alarm and you don't have sprinklers, what happens within 2 to 3 minutes? The fire starts to grow quite rapidly. And then roughly about 3 to 5 minutes, you should possibly have flashover, and then at that point, in that area, it'll get a bit out of control, and you will have serious doubts about anybody surviving, depending on the size of the property, etc. And if you have fire brigades local to the premises, you possibly have water on the fire within 10 minutes. I'll give you an example of that. In the Highlands of Scotland, there's only one full-time fire station, and that's in Inverness. The rest are all temporary. So if you can imagine, they'll get the call out saying there's a fire. They've then got to get to the fire station, get changed, get on the truck and get away. Now that could be 20 minutes or half an hour before they actually get there. So this is ideal situation. Oh yeah, that's the reason for installing sprinklers. Now, I like to talk about CDM regulations. CDM regulations enforceable by law. But information regarding the design of sprinkler systems and fire compartmentation must be set out by the principal consultant at the pre-construction plan phase. Now that can either be the sprinkler engineer or it can either be a mechanical consultant. Okay. But the mechanical consultant has to get information from a specialist in sprinkler installation, so they should seek advice from sprinkler companies or sprinkler consultants, preferably sprinkler consultants, because they'll tell you what you need to know and not what the installation company might want you to know. So the thing is, when a sprinkler engineer gets the consultant specification in, they may find some anomalies. And when he does that, he should actually get back to the principal consultant and tell him that there's issues. Some of these issues may be the wrong specification, i.e. it's not current, the wrong classification for the risk. For instance, a lot of consultants are classing schools as Ordnance Hazard Group 1. In some cases, they're Ordnance Hazard Group 3, potentially Ordnance Hazard Group 4. And the full building is not protected, as what it should be. Okay. But then again, there may be anomalies, and there's reasons for them, so it has to be best to check. So the sprinkler consultant must work with the building design team, maybe information, contractor, and the consultant, or the end user that may affect the overall design. So trying to get in early to get the full picture is very important to make sure that you get the proper sprinkler coverage. Yeah. Now, if there is any departures, they must be agreed. Okay. And when you get that, you should receive a document such as this from the sprinkler contractor. Okay. And that should describe that should describe the departure, the clause reference, whether it's a minor or a major, who's introduced it, the date it was introduced, and who agrees it. For instance, no zone valves on a floor of a tower block. Clause reference might be 5.1a. Now, we would consider that as being a minor because it wouldn't actually affect the operation of the sprinkler system because the water would still flow to the heads. Okay. Introduced by the consultant at tender stage, whoever it is, that was the date it was introduced. And this is the people who have been advised of it. So the consultant, the client, the insurance, building control officer, they all have to agree. And that's what a sprinkler contractor will ask for, or what it should ask for. So buildings over 45 metres with no special circumstances, for instance, that might be clause 4.5. Now, the way we'd see that as a major, because that could affect the design of the system. So buildings over 45 metres would require multi-stage pumps, etc. It's known as a high-rise building. Okay. So it's continued to use a consultant at tender stage. That's the date. And in that instance, consultant, client, insurance, building control officer, and possibly God. So we would look for that to be engraved in a brass plaque so we could put it on the wall to make sure that we're keeping ourselves right. But it has to be done at early stages to give the client a chance to remedy the situation. Now, if they proceed with the system, including the non-compliances, but they're not agreed at all, then I would say the sprinkler contractor is leaving yourself open to risk at a future date if there's any problems. Okay, so basically if the system fails in the future for one of the listed reasons, then you'll be covered, and the liability would lie with the consultant. So this is where sprinkler engineers need to start putting their fire engineering hat on. The fire triangle requires heat, fuel and oxygen, and that will create a fire. To deal with that, to put the fire out, you just need to deal with one element of the fire triangle. So for instance, you may have water coming on, which will deal with the heat. And whilst you're dealing with the heat, you're actually dealing with the fuel further on. You're taking out two parts of the fire triangle. Now, a byproduct of the situation where you get water on fire is you create steam. And when you create steam, it can actually wrap itself around the fire and suffocate the fire. So the effect that you're actually doing is dealing with the full three elements of the fire triangle. Okay. The smaller the droplets in the sprinkler system, is more effective it is with oxygen. And basically, if you can imagine a water mist system, finer droplets deal with the oxygen more than it deals with the heat and the fuel. So that's how water mist systems work. They deal with the oxygen, they suffocate the fire, and basically they work better in more confined spaces. The sprinklers require to be installed with other forms of fire detection and protection systems. Okay, so they should be installed along with automatic fire detection systems, such as air sampling systems, such as sniffer systems, linear heat detection, smoke detection, heat detection, thermal imaging, or explosive gas detection system. That's mainly industrial use buildings. Also, compartmentation. So it's very important that fire compartmentation walls are put in place. Also fire doors and fire sealant, because the sprinklers are designed to work in areas. You don't want the fire to get out of control and burst through walls and get to larger areas. Then the sprinkler system will be overwhelmed and it won't work properly. And then the other types of fire suppression system itself. We've got control mode sprinklers, which control the fire until the fire brigade get there. That's the most commonly used one. There's suppression sprinklers, which is your ESFR, mainly used in some warehousing. There's domestic and residential, which is BS 9251, which is a separate course that we do. Water spray systems are generally used in oil and gas, so they're there to protect pressure vessels, gas storage tanks, that kind of thing. Foam system is an enhancement to a water-based sprinkler system, where they're used for pool fires, where the foam's poured on top of the pool fire and it suffocates it. And then you've obviously got water mist system, which again is part of another standard. And it's not unusual to have buildings with sprinkler systems and gas systems inside server rooms, etc. So gas systems can be gas suppression, so that's gas suppression system, CO2, whatever it may be. You also get low oxygen systems, which is a system that will take enough oxygen out of the air to stop the fire starting in the first place. I think there's one of them installed in the British Library. And dry powder systems, that's your R102 systems over kitchen, hoods, etc. So sprinkler systems work in tandem with all this fire suppression and detection systems. So again, another example of a fire. Okay, so it's essentially to maintain a sprinkler system and also to have procedures in place in the event of a fire. Now, I've got the Ocado fire up here. Now, what happened basically here was the fire services report found the fire started at 20 to 2 in the morning, the 5th of February 2020, I think it was. So the fire detection system did not detect the fire as designed. So it was first spotted by an engineer at 2:15 in the morning. The sprinkler system started to operate within 11 minutes, but then was turned off by the engineer for 5 minutes. Now, what had happened when he switched off the fire was, unknown to him, that the fire had started in another part of the racking system. So within that 5 minutes, the fire had grown so significantly. By the time he switched on the sprinkler system again, the fire grew so big that it overwhelmed the sprinkler system. And it burnt down. So the fire service were on site for 4 days at a cost and the cost to replace the building would sit over £100 million. So it's very, very important that you get your procedures in place and people are trained to know how to deal with things. And that was the result. So quite significant damage. Well, total damage, total failure, total loss. I think it's been rebuilt, or it's getting rebuilt at the moment, however. Now, while we're talking about that, I just want to run through how sprinklers work. They work by removing heat from the fire, wetting the surface ahead of the flames, cooling the atmosphere around the ceiling to help protect the structure by producing steam which will reduce oxygen level. These all combine together will control or extinguish a fire. What you get is a sprinkler head like this, and the head will comprise of a body, yoke and arms. You've then got a frangible bulb inside which holds back a brass seating. Now that brass seating's got a little rubber ring in it, and then that holds back the pressure in the pipework. And then at the bottom of it you've got a deflector, and that comes in a whole array of different shapes and sizes. I think we'll touch on that later. Okay, so what happens is the bulb bursts by the heat, releases the seating, and the water comes out and creates a spray pattern. So the bulb, thermosensitive bulb, and that the different colours set to different temperatures. And as they heat up, as I say, they burst, you can see the seating coming away, and then you've got a spray pattern. So how do they work again? It's a case of pressure. So you'll have an amount of pressure at the head, depending on the type of system that you do. For an ordinary hazard system, it might be 0.35 of a bar. For a high hazard system, it might be half a bar. And for an ESFR system, it could be 3.5 bars of pressure. Now, as you put in the pressure here, it'll give you a spray pattern here. And you'll get droplet sizes such as this. Now, in a commercial system, it's 2 metres max from the wall. Okay. So if you increase the pressure here, what happens is it increases the head area, and it also gives you smaller droplets. When you've got the same K factor, which is the orifice of the sprinkler head. But again, you've got to be a maximum of 2 metres off the wall. Now, sprinkler systems are designed in the UK to LPC rules and BSEN 12845/2015. Yeah. Now, these consist of the main body of the rules, which is BSEN 12845, and then what you've got is annexes to the back of that, and it's Annex A to NA. It's not it's not applicable. It is actually an annex. Okay, so ideally you want to be implementing both of these. You don't need to implement the annexes. You have to specifically say that you're not implementing them. Okay. And at the back of that, you've got technical bulletins. Now, the technical bulletins are put together by a committee that comprises of insurance companies, the FPA, and these have been written to enhance the rules over time. They're not mandatory, and they're not used outside of the UK. However, insurance companies will ask for them to be implemented because there's a reason why they're there. Okay. Now, you will find other types of rules that are used in the UK. FM is factory mutual, which is American rules. That's the insurance company rules. NFPA is the National Fire Protection Association. Again, it's the American rules, so that's similar to the LPC, if you like. VDS is the German rules, and BS 925 is for residential and domestic. You've got other types of rules, however, you may want to look into that. A good British standard for consultants to use is BS 5306 Part 0, and that will outline the best system to be implemented in certain situations. So how do you select sprinkler heads? Sprinkler heads shall have a temperature rating close to but not lower than 30 degrees above the highest anticipated ambient temperature. The size of the sprinkler heads relates to the density of the installation. Spray pattern on the building risk and spray pattern depends on the building risk and layout of the structure, and that's been enhanced in TB 207 of the rules. The response of the heads also depends on the type of system installed, and that can be either standard response or fast response. Again, it's all highlighted in TB 207. Okay, so this is a table out the rules, and it tells you the colour related to temperatures that the building will be operating to. But it's important to note that different temperatures have got the same colour bulb. You really need to be specific on what heads you want to use. So get the temperature. When you're ordering the heads, you basically say, I'm looking for a black head at 227 degrees C, etc., etc. That's the glass bulbs. You also get fusible link heads, which is basically just solder, which melts between temperatures of, say, 80 to 107, and that'll be marked with that'll be marked white. Okay. One of the most important things is that sprinkler installations should be installed by third-party accredited companies. Okay. Now, there's three schemes. You've got LPS 1048, and they have a separate scheme for the residential and domestic, and that's LPS 1301. However, if you have 1048, the 1301 already gets included in 1048. There's FIRAS, which is the Warrington Certification Scheme, and they work on the same principle. And then you've got IFC certification. Now, if we just break that down, it shows, if you can see here on the commercial side, you've got level 1. The level 1 will allow you to design, install pre-calculated systems, including water supplies. However, everything that gets designed by the installing company has to be supervised. So the drawings get supervised, the site installations get supervised. So, and then level 2 is the same, except you can start doing base build jobs, and that's where you've got like sort of high-rise buildings where you're only protecting the landlord's area, but you're actually putting a zone into each floor for another contractor to come in and fit out the floors. You've got level 3, which allow you to do the same as level 1 and 2. However, at level 3, you can actually do full hydraulic calculated systems. You're then into high hazard systems. However, you need to be fully supervised on your high hazard systems. Level 4, they can do everything and they're self-certified. When you get into the domestic and residential, I think it depends. You need to do a certain amount of jobs, and if they're happy with that, you can then self-certify. You know, but it's worth to note that third-party certification in the UK is voluntary, of which reputable companies choose to demonstrate their competence and abilities to the clients. The independent third party confirming that the certified companies are competent and suitable to undertake certain types of work. So basically, that's why you should have third party accreditation. And that goes with water mist systems too. There is a fire risk scheme for water mist systems. And I think at the moment there's only, I may be corrected, I think there's only 7 companies on the water mist third party schemes. So we're going to move on now to the actual classification of sprinkler systems itself. So if you're a consultant and you're asking people to design or put together a price for a sprinkler system, this is information that you'll actually need to give the sprinkler company so that they can then put together a design and price the job or whatever you want them to do. So we need to know the compartmentation. We need to know the fire engineer report. The fire engineer report will compartmentise the building, and it will also state, or should state, what the classification of the sprinkler system is. Okay, it's the principal contractor's responsibility to do that. So between the mechanical or the principal consultant, not contractor, principal consultant should employ a fire engineer, and between the two of them, they should basically determine what the risk of the building is, the classification of the building. That's why it's important that they should maybe employ a sprinkler consultant at that stage to make sure they get it right, because they don't always get it right. We also need to know the building use, the structure of the building. The structure of the building can determine if you are putting void protection in. We also, when the sprinkler engineer is designing the building, he needs to know the steelwork, because the steelwork will determine the spacing of the heads. We also need to know the void depths. We need to know what's stored in the building, how it's stored. We need to know MEP service routes. Now, this is to help us route the sprinkler pipework, but also when you get MEP services and maybe additional sprinkler heads required to give full coverage. The classification of the system is generally supplied by the insurance company. Because at the end of the day, the insurance company are there to pay the bill if the place burns down. So, as I say, the principal consultant should pick that. However, he should consult with the insurance company, which is in the main rules, BSCN 12845. It quite clearly states it should be initial consultation with the insurance company. So density is measured in millimetres. Okay. Now, I don't know if you've heard, but you'll hear 5 millimetres a minute over an area of 260. So 5 millimetres a minute is literally the depth of water you will have on the floor after a minute. So if I say 5 millimetres a minute to you, the sprinkler system will deliver you 5 millimetres depth of water over that area. And the area, or the AMO, is the assumed maximum area of operation. So that's the assumption that the fire will grow to 72 square metres over a period of time, or 144 or 216. Okay. So basically, design density is measured in millimetres over a square metre. Okay. For example, 5 millimetres a minute over 72, which is ordinary hazard group 1. So a sprinkler system in that case would deliver 5 millimetres over an area of 72 square metres at maximum. So if you've got, for instance, the system running for 10 minutes, the possibility that you're going to have 50 millimetres of depth of water in there. So the compartmentation is a very important part of sprinkler design. So sprinkler are designed to work in conjunction with other forms of fire protection. Compartmentation of the building is essential to prevent rapid fire growth that might overwhelm the sprinkler installation. to a point where it cannot cope. Within BSEN 12.45, there are exceptions, such as you don't need to protect washing rooms or toilets. However, cloakrooms you need to protect. They've got not to be used for storage. Closed stairways, but not storerooms off the staircases and not used for storage. Rooms protected by other forms of fire suppression, so that'll be gas, water mist, etc. Wet process, such as end-of-line paper making machines. Rooms or compartments containing electrical power, such as switchgear, transformers, and used for no other purpose. Okay. It does not cover distribution boards. So what we're basically saying is that there are certain rooms you don't need to protect. However, when you're not protecting them, you need to put fire compartmentation around them. Okay. So you've also got necessary exceptions. Makes sense. Some areas, some rooms just will not like the introduction of fire. So silos or bins containing substances which may expand on contact of water. Okay. So industrial furnaces, kilns, salt baths, smelting, anything like that. So it indicates a hazard would increase by the use of water and the extinguishing of a fire. Areas, rooms or places where the water discharge may present a hazard. In all these cases, other forms of fire protection should be considered, i.e. gas systems. Okay. All of these measures need to be installed in accordance with the guidance set out in BSEN 12845 TB 206, and this is to do with compartmentation and passive fire protection. Now, you may find that what sprinkler rules ask for is over and above what building control asks for, and that's where you get a bit of banging of heads. So TB 206, I think that's figure 1, if I remember rightly. That shows you areas with sprinklers and areas without sprinklers. And when you go to TB 206, this will guide you to the tables that need to be consulted when you're determining fire resistance of walls, doors, etc. between buildings. Okay. So the shaded areas in this instance are sprinkler compartments. As you can see, the compartment wall 4.5 in table 2 between the two shaded areas, that should be table 1. That's a mistake in the British standards. Okay. And the unshaded areas are areas that are not protected. That just refers you to the tables and the clauses that need to be read. It's worthwhile reading this. For instance, table 1, this is recommended fire resistance between fully sprinklered compartments. Fully sprinklered compartments, so that's where you've got sprinklers, walls between two sprinklered areas. So for instance, if we've got a residential, hospital or institution, and it's on the ground floor or upper floor, it's up to and including 18 metres high, I will need a fire resistance of 90 minutes between two sprinklered areas. That's what it says, that's what the sprinkler engineer will look for. And it goes on and goes on, so you'll see here car parks for light vehicles, basement including floors up to 10 metres deep, not applicable. Ground and upper floor up to 5 metres, 15. Okay, 15 minutes. And then you've also got clauses against that. But you just need to make sure that you read the clauses too. But important to note that no part of an unsprinkled building or sectional should be located vertically below a sprinkled building. Okay. Or exception and permitted necessary exceptions as previously mentioned. Right. Now that's important because you do tend to get, for instance, there's a rather large retail shopping centre getting built in Scotland at the moment, and everything's protected from the ground floor up, but there's 3 stories of car park below, and that's not getting protected. and with some of the fires that have been going on recently in car parks, that's quite worrying, so the chances are that could affect structure of the building if it got to a high density fire, which may affect the actual structure of the full building. I think that's the reason why they're doing it. Okay. Right, so as I say, for example, a basement car park below a sprinkler car park must have a sprinkler system, such as a shopping centre or an office block. So when the fire engineer's putting that together, he's got to take that into account. Otherwise, you're going to end up with a non-compliant sprinkler system, etc., etc. A lot of the time in that situation, your sprinkler pumps and whatnot are actually inside the basement. And when you've got that situation inside the basement, the sprinkler mains are running through unsprinkled areas. What then will need to happen is that these sprinkler pipes will need to be protected with at least 60 minutes of fire-rated board or fire-rated spray or whatever. Not just the sprinkler pipe, the hangers themselves too. No point in just protecting the pipe. If the hangers melt, the pipe will just fall down. So Table 2 in TB 206 gives the fire resistance between sprinklered and unsprinkled areas. Again, residential hospital or institution, ground floor, up to 18 metres, again, it's 90 minutes. Okay. Righty. But you need to follow this table. Now it's worth to note that if you look at 3 office and you come across the ground and upper above 30 metres and an office block over 30 metres, it's not permitted. The fire resistance, that means that you've got to have fully sprinklered buildings. Okay. And it goes on and on. So you can look through TB 206 if you get your hands on it and see what you can implement. Okay. The building use. The use of the building will determine the design parameters of the sprinkler system. To determine the design parameters, you'll need to know what the building is being used for, the height of the building, storage within the building, what it is being stored, the commodities, how are the commodities being stored, and you need to then take that information and use TBs to determine what you're actually having to put in. So for instance, these can relate to hazard classifications or hazard occupancies. So ordinary hazard group 1, ordinary hazard group 2, ordinary hazard group 3. Okay. Then you get high hazard process. Okay. And that goes high hazard 1, 2, 3, and it's actually 4. So high hazard storage occupancies, and that all depends on the types of storage. That's ST1, which is block storage, ST4, which is palletised racking, etc., etc. Now that's all detailed out in TB 234. You also need to know the classification of the goods, which you'll get from TB 217, which is it details out. You'll get tins of beans in a box, etc. Yeah. And we're going to run through this shortly. So for instance, what we have here, primary schools, offices, hospitals, hotels. Okay. So if you're protecting them, you're looking at an ordinary hazard group 1 system. So that would be classed at 5 millimetres a minute density, so that's the depth of the water on the floor, over an area of 72 square metres. Now that would be for a wet system. Now a wet system is fully charged with water. However, you can install dry systems, so they're charged with air. And the idea is that it takes a bit longer for the water to get to the point where the fire is. And because it takes that little bit longer, so it needs to disperse all the air before the water gets there, your fire area may grow from 72 square metres up to 90 square metres. And at that point, you need to have a pump that will give you more water over a bigger area. Okay, so this one here is primary school in East Kilbride, near Glasgow. Ordinary hazard group 1, that was property protection. It was a pre-calculated system. which is predetermined pipe sizes and tables, and predetermined pump sizes and tank sizes you get from tables. That one had a single electric pump and a full capacity tank. Another example, car park. Ordinary has Group 2. You're looking at abattoirs, car parks, museums, and chocolate factories. Okay, so that what happens here is in ordinary hazard, you'll find that the density is always the same, it's just the area of operation gets bigger. So for instance, in ordinary hazard 2, it's 5 millimetres a minute over a assumed area of operation of 144 in a wet system, and then when you go to dry, it's 180. Dry systems are always 25%. The area a dry system covers is always 25% larger than what a wet system is. Okay, so this is an example. So it was an office block with a multi-storey car park to the underside of it. Ordinary has Group 2. It was property protection and it was an air system. Fully hydraulic calculated, so that has to be run through a program. I think it was Canute. It had a diesel and electric pump, so it had a superior supply. It had a split tank and it was full capacity. Then we move into Ordinary has Group 3. You're then looking at retail, high schools, production farm buildings, etc., etc. And that increases the area of operation from 144 to 216 square metres for a wet system. And then 25% bigger than that, dry system at 270. The example I've got here is the Marks and Spencers at Glasgow Fort. Ordinary has a Group 3, that was life safety. The wet system, it had a containerised pump house, I believe it's supplied by Grundfos, electric and diesel, and had a split tank. Okay, now schools. If you go to the technical buildings for schools, DB 221, it will generally say that schools are protected to Ordinary has Group 1. But there's also a recommendation in there that a fire risk assessment should be done. So what they tend to say is that smaller schools are Ordinary has Group 1, but when you get into larger schools, you'll need to start looking at putting up to Ordinary has Group 3. Now, when you look at schools, schools have always got plant rooms in them. And plant rooms are classed as Ordinary has Group 3. And because you've got that, you're automatically going to take it up to Ordinary has Group 3. However, it will depend on the size of the plant room and depending on the size of the area, which could determine the Ordinary hazard classification group. So for instance, Wick Academy, we could determine that the school had different areas, different hazard classifications. So for instance, Ordinary has Group 1 was a general classroom, and then Ordinary has Group 2, library with some stores in it. Ordinary has Group 3, the plant rooms are rather large in that school, as you can imagine. Okay. It was life safety, or Annex F. It was fully hydraulic calculated, and one electric pump, one diesel pump, two tanks, full capacity, and it also had 13 zone checks in it. Okay, which basically zones the system in areas, and that's what you need to do with life safety. And another one here. Now, when you get high-rise buildings, anything over 45 metres from the lowest to highest head is classified as a high-rise building. Okay, and when you get to that point, even if it's an office block, when an office block is usually Ordinary has Group 1, when it gets to high-rise, it's automatically Ordinary has Group 3. Okay, so for instance, this here was 1 West Regent Street, and that was over 45 metres. So it automatically went to high-rise building. Okay, so it was Ordinary has Group 3. That one had 13 number zones in it, and each zone was a maximum of 2,400 square metres. It also had a multi-storey car park in it, so that was a dry system. Okay, and that was Ordinary has Group 2. Okay, it was a pre-calculated system, 2 electrics and 2 diesels, split tank. Now, when I say 2 electric, 2 diesels, that was actually multi-stage pumps. which is what you need to do in 45 metre systems and above. And then we're kind of moving into the kind of higher risk side of things. So Ordinary Hazard Group 4 would cover alcohol distilleries, cinemas, concert halls, film and TV studios. Okay. Now, 5 millimetres a minute over 360 is actually for the wet system, and the dry system would be 25% bigger than that. And where we used this was John Dewars in London Road, Glasgow, and that was a gin bottling hall. Okay, so that was a wet system, property protection. We actually used a live tap system on that one because we were extending an existing system, which meant that the actual warehouse was never without sprinklers during the full install. It saved us an absolute quite a lot of time. It saved us a lot of money using the live tap system. So on that one, we had 3 half-duty pumps and 3 full capacity tanks. Now the half-duty pumps, because we had such a high flow on that site, basically you had 2 pumps that gave us, I think it was 14,000 litres a minute. So each pump gave us 7,000 litres a minute at 8 bar, if I remember rightly. So when you get half-duty pumps, you get 2 pumps to double the flow but keep the same pressure. And that's why you use half-duty pumps, because it's a lot cheaper to install half-duty pumps on higher flow jobs than it is to install just 2 normal pumps. Now, moving away from ordinary hazard, you're then into high hazard process. Now, high hazard process is areas where you're producing high hazard materials, for instance, fireworks manufacturers. But this one, for instance, was DS Smith in Livingston, and what they done was they put together kind of foam packaging for TVs, etc., etc. So they had the raw material of the little polystyrene balls, and that there is the polystyrene balls are very flammable. So it then became high hazard 4 packaging. Okay. Now when you get to high hazard 4, it's a deluge system. Yeah, and that's when you've actually got every single head going off in that area. So it's segregated into smaller areas so that we can control the fire. Again, that one had 2 diesel pumps and full capacity storage tank. Moving on again, you get into high hazard storage. Okay, and when you get to high hazard storage, talk about warehouses. The warehouses are a huge subject. I'm only going to touch on one part of it. Well, there's actually we have got another presentation on high hazard storage and warehouses that we can share with you at some point. So basically, this one here was a job I done in Dublin, where we had a roof and rack system. We had 2,000 heads at the roof and 18,000 heads in the racks. Okay, fully protected. It was high hazard storage 1, storage category 3. We had 10 millimetres a minute at the roof and 9 heads in operation in the racks. All depends on the space in the dials when you come to the racks. That had 3 diesel pumps, 2 full capacity tanks. Now, if I can remember rightly, we had quite a high flow in this job because sections of the racking were actually aerosols, and there's specific rules along with aerosols, and you need to take that into consideration. You're looking at 30 millimetres a minute at the roof. If you can imagine, every minute you're going to have 30 millimetres of water on the floor. Quite a lot of water, plus all the heads operating in the racks. I think if I remember rightly, you were getting somewhere in the region of 10,000 litres a minute out of the pumps. Quite a lot. Quite a lot. Okay. As I say, it's a huge discussion, this one now, because of the Ocado fire, etc., other fires. You find that basically people take into account the different types of rules, where they maybe use the FM rules in the racks, and they might use LPC rules at the roof or something like that. So it's a bit of a mix mash, and people are still trying to get it right. Worth to note that FM and NFPA have got huge testing facilities in the States, and they actually do live fire tests. So generally what comes out of the FM rules will follow on to the LPC rules, because presently the BRE or Warrington don't have testing ability to test fires in live fire situations. So hopefully that gets changed shortly. We're going to move on again to ordinary hazard classifications. So ordinary hazard systems can be sized using either the pre-calculated method, which is predetermined pipe sizes and tables, pumps, tanks, etc. Or you can use the full hydraulically calculated method. Now that means that you need to actually put all the information in the system into a calculation program and then start putting together areas of operation and stuff like that. Okay, so as I said, pre-calculated systems are sized with the use of predetermined pumps, tanks and pipework tables, and you get that from BSEN 12845 and the LPC, the technical bulletins. Okay, now we do have another module in that, module 2. Full hydraulic calculations are designed by the use of a calculation package such as Canute. You've also got other calculation packages, FireCAD or AutoSprint. Right, this method is more advanced and requires an experienced designer. And again, we cover that in another module. A building may have several grades of system, so ordinary hazard occupancies within the building. These can be classed in each area. However, the water supplies must be sized for the largest risk. Like, say, for instance, when I was talking about Wick Academy, that had ordinary hazard group 1, 2 and 3. The water supplies were sized to ordinary hazard group 3. Where do you get this from? So I'm going to use Wick Academy as an example. So this is the tables from Annex B, I think it is, which is also TB 217. Okay. So you'll see here, when you go here, you'll find classrooms and it says schools. Right? But you should also consider TB 221 when it comes to that. Okay. Now, libraries are also in there, excluding bookstores. When you got bookstores included there, you need to move it up to ordinary hazard group 2. And then you get plant technical rooms, which are in there. I'm using a scroll because these are the easiest ones to do. Okay. So labs, science classrooms, etc., they're in there. And then if you get some schools with theatres in it, and they could fall under ordinary hazard group 4. As you can see, you draw it down, and that's where you get it from. So the highest risk on this site is a theatre, ordinary hazard group 4. Okay, and that the water supplies would be sized for ordinary hazard group 4. And then you move through some more. You find that shops and offices, apartment stores are under ordinary hazard group 3. Exhibition halls, ordinary hazard group 4. Timber and woodworking factories under ordinary hazard group 3. Sawmills are under ordinary hazard group 4, but they also fall under high hazard process. Obviously, you should be seeking the advice of the insurance company, because at the end of the day, they will pay the bill if the place burns down, and if they're not happy with the original design, they may not pay for the rebuild. Then we've got another one, Kingspan factory in Wales. Obviously, Kingspan is basically they build the cladding for the buildings. Okay. Now, this would be considered as high hazard process because they're making something. It's a process. Okay, and they use gases and flammable liquids to produce the panels. Okay, the sheet metal working factories, injection moulding. So basically you've got two sheet metals getting moulded together with an injection of chemicals. So that would come in here. Okay, and that would be high hazard process 1. Okay, and once you know where you've got, once you know the hazard classification for ordinary hazard and high hazard process, you would use TB 229 table 2. You would follow down the hazard classification here. So ordinary hazard group 1, 2, 3 and 4. Okay, So Kingspan Factory Wales, high hazard process 1. So for the high school and wick, you move along, the density is 5 millimetres a minute, and for a wet system it's 360, and for a dry system it's 450, and that's the maximum area of operation. The pumps would have to be sized for 5 millimetres a minute over an area of 360. So a quick working out of that would be the density times the area would give you the flow required for the pump. 5 times 360 would be the density, the flow required from the pump. You're getting quite a lot of water at that stage. Okay. Now, if you look here at high hazard process 1, 2, 3, and 4, you'll notice that the AMAO, maximum assumed area of operation, is the same, and it's the density that goes up in high hazard process. So for high hazard process 1, you get 7.5 millimetres a minute over 260, or 325 if it's a dry system. And then you'll see for high hazard process 2, it's 10 over 260 and 12.5 over 60. And then, like I said, when you've got high hazard process 4, it's a deluge system, so that's every single head going off. So that's like manufacturing of packaging. It's also fireworks factories, that kind of thing. High risk. Okay. So, worth to note, dry systems are used when there is a chance of the water freezing or extreme temperatures. Okay. The increased area is to cover the time taken to release the air of the system. Okay. So that's where all that comes from. To determine the classification of goods, you'll need to refer to Annex C and TB 217. The highest fire risk of the commodities should be used to give the categorisation of the goods. It's best to seek the advice of the incumbent insurance company to classify the goods in storage within the warehouse. Okay. The density and area of operation is determined through a series of tables that require a classification of storage and types of storage. And if you fall out of these parameters of the allowable storage heights, okay, I've lost my train of thought. Allowable stack heights of the goods with roof-only protection, you'll need to install rack protection or consider ESFR, which we don't really cover here. Now, ESFR is air suppression fast response. That's a control mode of sprinklers installation. What that basically is 12 heads in operation at the roof. And if you can imagine, you've got 12 hose reels at the roof shooting water straight down to the floor. Because they operate at 3.5 bars. You've basically got hose reels shooting a lot of water straight down to the floor to basically extinguish the fire. And they act really quickly. And you're not talking about 5 or 10 millimetres a minute, you're talking about 30, 40 millimetres a minute density on that. So for instance, if you look at this, and we consider what the highest fire risk here is, you look at it, that's a washing machine, that's predominantly metal. However, you've got expanded plastic in there, and unexpanded plastic in there. So expanded plastic is packaging, unexpanded plastic is like plastic sheeting, plastic cups, plastic toys, that kind of thing. The higher fire risk here would be the expanded plastic. So you get rolls of corrugated cardboard stored vertically. Now that differs from other types. So when you've got it stored vertically, you've got, if you like, a flue in the middle of the rolled cardboard, so the fire can get inside it and catch quite quickly. And this is what happens. You go to TB 217 and you'll find tables like this. And as you can see down the left-hand side, it gives you the product, gives you the category and some notes. Okay, so you'll see here that cardboard rolls stored vertically, rolls stored horizontally. I've got different categories. So for instance, cardboard, except corrugated, if they're stored horizontally, it's category 2. If they're stored vertically, it's category 3. And this all came about live fire tests, possibly in the US. Anyway, roll stored vertically, that's category 4. Okay. Corrugated cardboard, where you've got a bit of free movement between the bits of paper. Cardboard's got air inside it. The fire can get into the gaps and then catch quite quickly. Okay, and it keeps going on and on and on. Okay, and you'll see here that, for instance, flour and sacks or paper bags, category 2. Foods and tins and cardboard boxes and trays, category 1. So wooden furniture, category 2. Okay. Hemp, special measures such as increased area of operation might be required, but however, it's category 2, etc., etc. That's where you get the categorisation of goods. So, again, there's some more. TB217, in a little bit more detail. So, alcohol is always a big one, especially in Scotland, where you've got, for instance, alcohol with a alcohol percentage of less than 20 in glass or plastic bottles and cardboard boxes, category 1. If it's over 20%, it's category 2. Okay. Beer, category 2. Keep going on about alcohol. And then you go down again. Okay. So that gives you an idea where to find it. So if you're planning to look at that, get into TB217, look down the left hand side, make sure you note how it's been stored, and then that'll give you the category of the goods. Okay. Keep going on. Table 1 continued. Okay. So, for instance, you get stored paper, stored flat. Now, that's actually quite a low risk because that'll burn the externals of the blocks of paper, but there's no gaps or no air to get into the middle of it. So, what you're going to find is that it's surface fires. Okay. We look here, paper. That's weight, 5 kilograms. We're all stored horizontally. That's like newspapers, etc. That'd be category 2. And then that's table 1 continued. So it's the same again. You just work your way down. You find out what you've got, keep doing it. Okay, so you've got, if you look here, you've got timber sawn, not in ventilated stacks, category 2. Ventilated stacks, category 3. Timber unsawn, category 2. So if the goods are not listed in Annex C or TB217 tables, then you can use the flow charts, graphs and tables in T117 to work out the categorisation of the goods. Many of the goods have their own specific technical bulletins and need to be followed separately, i.e. palletised pallets, alcohol storage, flammable liquids, all that kind of thing. However, you need to really consult the insurance company on that one. You'll get this here, so you'll find if you follow the flowchart, are the good listed as a special hazard? So if you look through the technical bulletins, you then refer to the technical bulletin. If you come down, no, the goods within the limitations set out in table T1, yes. Are the goods listed in that table? Yes, use that. No. Do the goods plus packaging contain plastic or rubber? No. Consult the authorities. If they are, you want to look at Annex B. Okay. Now, if you are going to use Annex B, which is basically Figure 2, and also the tables associated with it, you need to know specifically what you're playing with. You need to know if it's expanded plastic or unexpanded plastic. See, your client has to tell you exactly the percentages that he sees it's going to be going into here, because that will determine the material factor. Okay? For instance, I'm jumping back to this. The washing machine goods, Ormer has group 1, table CT1, that's basically steel. Okay? Expanded plastic will get 35% stored goods. Unexpanded plastic film. So because that's such a small percentage, it burns away quite quickly. We can ignore it. So the biggest risk here is going to be expanded plastic. So we go down here. It's expanded plastic, so it's down here along the bottom. That's between 25 and 40. So it's material factor free. Okay. You would then go in here and go, okay, material factor free, banded plastic, category 4. And that's generally how you would use the Annex B. That's generally how you would use TB217B. Okay. Now, what we're going to talk about is types of storage now. Well, along with the category, you need to know the type of storage. And from that, you can use the tables in TB234 to determine the density of the roof. So this is ST1, which is block storage. Okay. And that's where goods are basically stacked on top of each other. And what happens there is when you get goods stacked on top of each other, you get very little air between them. You're going to end up with surface fires, and the heads of the roof will contain that quite quickly. ST2 and ST3 is post pallets. That's where you get the pallets that actually slot into each other, that forklifts can lift them off and take them away, etc., etc. So that might be carpets, etc., like that. Okay. And what you get with that situation is you've got a bit more space for the fire to grow. So the fire tends to follow this type of situation. And when you've got multiple rows, it can spread quite quickly. ST4, palletised racking, we'll all have seen that. So this is where you've got a distribution warehouse, and in the distribution warehouse, you've at the front area is the distribution part, which is where they sort all the stuff out. They go into trucks, and then you've got the storage part at the back of it, where you get racks. Okay. So in this situation, you're going to have roof protection at the front end and roof and rack protection at the back end. Okay. So if you look to the diagram to the left, you'll see that's without in-rack sprinklers, so the fire can grow quite rapidly through the storage racks, the palletised racking. It's got lots of areas to grow. However, if you put rack protection inside, it contains the fire inside the racks. Okay. So when you've got a situation like this, you may have something like that. But ST8 is double deep palletised racking. So that's where you've got the rollers, where you basically push the pallets from the front up to the back. And when you get a situation like that, you need to have many, many heads in operation to make sure that the fire is contained. Okay. Other forms of storage are ST5, which is solid shelves, single solid shelves, up to 1.2 metres wide. ST6 is double shelves. If you can picture supermarkets, that would be ST5 and ST6. Okay. General protection at roof. General protection at roof only covering ordinary hazard protection. Maximum storage details in table 1. So basically, if you're getting the maximum storage height for these two, you need to use table 1. Otherwise, you need to go into TB234 and use ST15 and ST16, which has been updated recently. Okay. You've also got ST8, 15 and 16, generally have in-rack protection, okay, which is covered in another module. Okay. So for instance, this one here, you've got S1, just block storage, just sitting on top of each other. Category 2, we got that from TB217. Category of goods is what you've got, and the type of storage, S1, S2, 3, 4, is actually how you're storing it. You've got to use that information to find the parameters of the sprinkler design, i.e. 5mm over 216. Okay. You would get that for table 1, or you move into table 2, 3, 4. So then we move on to the building structure. Structure of the building can play a massive part in the overall design of sprinkler systems. Things to consider are the fire resistance, structure of the building and angle of the roof can alter the design of the pipework, also limit the type of the system. So for instance, in a roof and rack, in a high hazard storage roof, I think the maximum angle of the roof is 10mm. The height of the building will determine the system requirements. Okay, and potentially add additional densities at the roof. Right. So when you've got storage and you're only protecting at the roof, you need to contain storage within blocks. Okay. So for instance, if you have ST1, ST4, this one shows ST4. If you look at the top corner here, see if I can get my little pointer out. So for instance, here, what we've got ST4 racking, so that's a single rack, a double rack, and a double rack. Now, you can't have ST4 racking like this. You have to have a minimum aisle width of 1.2 metres between them, and they can't cover any more than 150 square metres high hazard. Okay, for ordinary hazard it's 50, high hazard is 150. Now, if you've got a firewall here more than 2 hours, you can store right up to the edge of it. If that's non-fireproof, so if that's combustible, you need to be at least 2.4 metres away from a combustible wall. Okay. So again, this one will be the same, 150 square metres. However, you need to be 2.4 off that wall because it's combustible. Okay. Your areas can be a different shape. Instead of being square, it can be right along the one length of it, like that. Okay. So that's basically that. And that's TB234 figure 5. I'll just run through that now. The maximum height above the storage and roof protection is determined in a series of tables, TB234. There are limitations to the structure of the buildings for roof protection sprinklers, limitations to the area of the storage and the floor, where there has to be a 2.4 metre well height to limit fire spread. The maximum block sizes for store and high hazard applications is 150, for ordinary it's 50. So between each block you need to have 2.4 metres as a fire break and 2.4 metres of a combustible wall. The maximum ceiling gradient in high hazard storage, 10 degrees. In installations where the slope exceeds 10 degrees, the following alternative solutions may be considered. If you get a ST4 type racking, intermediate in-rack sprinklers can be provided. Okay. The impact upon the area of operation of the sprinkler system shall be taken into consideration. Provisions for the area to be adjusted accordingly. You've got to consult with your insurance company on that to make sure that they're happy with what you're doing. If they're saying you can't do it, consult your insurance company. Righty. Now, what we have when we've got roof protection only, stored items. So the stored items is the commodities, so that's your category 1, 2, 3, 4, and the way they're stored is the storage types, that's ST1, ST2, etc. It's irrelevant in this slide. Okay. So where A is the actual storage of the height, so that's what you're actually storing to. B is the allowable storage of the goods. So when you find that you're going to be using a certain density, that'll allow you to store up to, say, 4 metres, but your actual storage of goods maybe only 3.5. Okay. And C, between the allowable storage, the height of the sprinkler heads is a maximum of 4 metres. Okay. If your C dimension is greater than 4 metres, you need to do something to deal with that. You can either install a ceiling or a mezzanine floor so that you're still achieving 4 metres, install rack protection, or you can increase the density of the roof. So we're going to look at this one here. This was a job, again, in Dublin, where we had quite a big area. So we've got a roof with protection in the roof and the racks here, but we've also got a mezzanine floor here and a mezzanine floor here. Okay. The density above this mezzanine floor was determined by the allowable storage plus the height, the difference to there. So actually we increased the density here to cope with that. and underneath here the density was fine because we're less than 4 metres between the allowable storage and sprinkler heads. But then again, you've got the distribution warehouse part of it, so that there was actually increased too quite a bit. Okay. Electrical goods, not metal and heavy duty cardboard boxes. So that's your commodities again. Okay, so that's how it's stored. Category of goods. So for SD1 storage, category 3 goods. Table 2, so this is just for block storage. We've only got roof protection only. Category 3 goods. Actual storage is sitting between 3.5 and 4.1. The density of the roof there would be 12.5. You always take the higher. So if we are sitting at an actual storage of 3.6, we then need to go to the allowable storage height of 4.1. Okay. That's 12.5 millimetres density over an area of 260. And you get that for table 2, TB23. Okay. There's different tables for different storage types. For instance, table 3 is for ST2 and 3, table 4 is for ST4, etc., etc. Okay, so that's your design parameters there. So for that instance, it would be 12.5 millimetres a minute over 260. How does this work? Right, so we get Cat 3 goods here sitting on top of the mezzanine floor like that picture showed. That's my actual storage height of goods there. And that's my allowable storage height that we just took, so that was 4.1. And that line there would show the 4 metres above the allowable storage height, which means I've got an area to make up, so I'm going to add density. So what we can do is, the first metre above that 4 metres, we can add 2.5 millimetres density. And the balance is 1 millimetres a minute. Okay. Well, let's run through this again. Actual storage height is 3.7. Allowable storage height is 4.7, we're saying. Okay. We're getting 12.5 over 260 at that point. That's my density. We're 4 metres above here, which means we're 6 metres difference between the top, the maximum of 4 metres to the sprinkler heads. Okay. So due to excess height of 6 metres, we have to add density. The first metre adds an additional 2.5 millimetres a minute. And the balance is 1 millimetres a minute. Okay. So we need to add an additional 7.5 millimetres density onto a 12.5 millimetres density. So my actual density of the roof above that mezzanine floor to cope with the height, 20 millimetres a minute. The design parameters above the mezzanine floor would be 20 millimetres a minute over an area of 260. Okay. Now, same again, same philosophy. When you've got table 4, but this is the maximum permitted storage heights for palletised racking, or beam pallet racking, whatever you want to call it. You've worked out the category of the goods, so it's tinned goods and cardboard or aerosol, whatever it is, you've worked that out. We're saying it's category 3, according to 3.2, we've got to go to 3.7, which tells me that in a beam palletised racking, we've got 15 millimetres a minute over 260. So we're increasing the density with that type of storage. Okay. Righty. So if we went back to the previous slide, the density, if we were using ST4 racking on that density, our starting point would be 15 mil over 260, it wouldn't be 12.5. So the actual density required for that system, with that type of racking, would be 22.5 millimetres a minute over 260. The different types of storage arrangements can increase the density of the roof. Okay. This is your typical in-rack storage. So what you've got a pipe running down here, you might be able to see it, and at every other level you've got pipe running in. So in here you'll see you've got pipe running right down the centre between that's called the longitudinal flue. you have a sprinkler pipe running right down the middle of that. This one here is actually, that there is a cage, so inside that area is the aerosols, and that's to stop the aerosols basically flying all over the place. However, in-rack protection looks something like that. Okay. When you get in-rack protection, you have to use figure 2, and it works something similar to your maximum of 4 meters. You need to use table 5 on this. So your A dimensions, your actual storage height, your B dimensions, your allowable storage height. And when you've got your allowable storage height, you need to use here. So category 3, if you've got, you can work it back here or work it whatever. So if your B storage height is say 3.2, you need to have 12.5 millimeters at the roof over 260, etc., etc. So if you've got 3.5 meters from the line of the top sprinklers to the top of the storage, 15 millimeters at the roof at 260. Now the important thing here is that C dimension is not allowed to be more than 4 meters. Okay. Now, if you can't achieve that 4 meters, okay, what you actually need to do is put another row of sprinkler heads at the top level of the racks, above the top level of the stored items. Okay, that's what you need to do. Okay. The voids. Enclosed Baldwin voids made from non-combustible materials and contain no MEP services need not be protected. Voids are over 800 need to be sprinkler protected. Voids under 800 millimeters and compartmentised by fire barriers of an area no greater than 250 square meters need not be sprinkler protected. Voids which vary in depth and have a measurement of over 800 in one part of it need to be fully sprinkler protected throughout, even if the other area is less than 800. However, if you fire compartmentation at 2 depths, you only need to protect the deeper part of the void. Voids used as air plenum shall be sprinkler protected. The fire alarm system shall shut down fans in the event of detection of smoke, stop the spread of fire. And in schools, voids are protected depending on how they're constructed and what's actually inside the void space. Buildings made from combustible materials, wooden frames, need to be fully protected no matter what's in the void space. Okay, and a building made from non-combustible material, which is brick, block, steel, etc., etc., and not wood, and where there's electrical cables greater than 230 volts and have trays greater than 400, so that's single or multiple, but they add up to over 400 millimeters wide. Void protection should be added. All non-combustible materials must have a Euroclass A1 fire rating, such as the structural lagging. Okay, now we're getting near the end, but what we're going to do now is run through the types of systems. Okay, and this is the last part of it, so you'll be glad to hear listening to my boring voice. So we're just going to recap on a couple of things. That's a sprinkler head. Okay, so you've got the frame, you've got the deflector, that's a pendant head, you've got the black glass bowl, etc., etc. And that's on a ceiling. That's the type of hedges you use in the ceiling. And then you've got a two-piece rosette, usually made from steel. Control mode sprinklers can be conventional, CUP, spray, SSP or SSU, sidewalls, concealed. Suppression mode sprinklers can be ESFR heads. Now, conventional heads are shaped like this guy here. Okay. Now, what that does, the spray part of that is more like a ball. It will throw 40% of the water up the way and 60% of the water down the way. And you've got spray pendant heads, spray upright heads. That's your spray upright head, and that's your spray pendant head. The spray pendant head must be installed pendant down the way, and your spray upright head must be installed upright. Okay? Now what they do is they throw 100% of the water down the way. Okay? You've also got sidewall heads, which is this one here and this one here. That's a horizontal sidewall. You'll see a lot of them in hotel rooms on the walls. Don't hang your jacket off them. And then the upright ones here. Other variants are concealed, recessed, dry pendant, and ESFR. Concealed heads are the flat plate type. Recessed is where the heads are actually on the two-piece rosette, but they're kind of just took into the ceiling slightly. Dry pendants are used in dry systems, and ESFR used in early suppression fast response systems. Types of systems you get a wet system. So a wet system is preferred. Okay, there's less chance of freezing in the building, that's when you use it. Dry systems used where there's a chance of freezing or temperatures over 70 degrees, so cold stores. Whiskey warehouses use them a lot. Reaction systems used when there is such a chance of accidental damage or high value areas, okay, such as servers. Now that means that you need to have an operation of the smoke fire alarm system before it opens up the sprinkler system, and then once it opens up the sprinkler system, then the sprinklers can activate, and they just act like a normal type of system. Deluge systems used for high risk areas such as tank farms, and that's where every single head goes off. And then foam enhanced systems, that's standard sprinkler systems with a foam. So you may have a bladder tank which feeds 1 or 3% foam into the system and gives you a blanket over a pool fire. Okay. Such as whiskey warehouses or petroleum. Right. That's your typical wet valve. And what you'll get now with a wet valve is a pipe coming up. At that point here it tees off, and that's called the bypass line. You've got a stop valve here, then there's an installation control valve, then another stop valve here. Now why we've got this in is that when we want to maintain this valve, we will shut this valve and shut that valve. We'll then open that valve. We've then still got a sprinkler system in activation because the water's just going to bypass the installation control valve and still feed the system. We can then drain this small part of the system, take off that cover plate, do whatever maintenance needs done, put it all back together. Makes it quicker, don't need to drain the system, and it's easy to put back online. So when we're finished and we're happy with it, we will open that valve, and then shut that valve. And during the maintenance, we've always got a sprinkler system. Yeah? Always. Now when you've got multiple sets of valves, what you can have is a combined bypass valve running along the back. You may find that in big warehouses. Right, so how does it work? Wet systems work such a way that the alarm control valve is here, and what you've got with the alarm control valve inside it's called a clapper. The reason we call it a clapper because it makes a clapping noise, nothing more than that. And the clapper sits over an annular ring, and on that annular ring there is a tap which then feeds over to a retard chamber, up to a pressure switch, and a gong, a water motor, an alarm gong. Now the idea is that when the pressure above is reduced because a sprinkler head goes off, pressure below which is higher than the pressure above will open up the clapper. This pipe will then fill out to the retard chamber, set off the fire alarm which tells the fire brigade there's a fire, and then sound an alarm gong. Okay. We'll get a sprinkler head in activation. Pressure above is reducing, so the pressure below is starting to raise the clapper, as you can see here. And at the same point, you'll have the annular groove filling up and the water starting to go down this pipe here. Okay, and it's keep going, and it starts to fill up the retard chamber. It's worth to note, the retard chamber there is for false alarms, and it can minimise false alarms, especially in Towns mains bed systems, where you get fluctuations in the main. Anyway, so we've not got a false alarm here, it keeps going. The clapper's now fully open. The water's basically right up It's got to the pressure switch, and what it's doing with the pressure switch, it is pushing the two plates together in the pressure switch, so you get contact, and when you get contact, that sends a signal to the fire alarm. Then it moves through into the bell. So we're keeping going and we're keeping going. The jockey pump's kicked in by now, possibly the main pump. It basically is then rotating the turbine within that, and you've then got a gong sounding an alarm. And that's basically how a wet system works. Okay? So the annular groove, it's not a very good picture of that, however, you'll see here that's the clapper and the annular groove's actually in here. Okay? Now on wet buildings you can zone them. Now you can use multi-storey buildings or you can use life safety buildings. Two ways to do zones. You can actually do it manually or you can use zone checks. Okay? Right? Zones, when you're zoning a building, all areas have to be sprinkled. So when you're zoning a building, the maximum area one installation control valve can cover is 120,000 square metres. For a property protection zone, it's 6,000 per zone. Okay, that's 20 zones. And for a life safety or an XF, it can be 2,400, which is a lot more zones. My mental maths will not allow me to work that out. So, no zone system shall exceed ordinary hazard group 3, nor cover more than one floor level, except under a mezzanine of 100 square metres. Worth to note, you can't actually zone car parks. Car parks have to be sitting on their own installation, usually dry systems. Now this is a manual way of doing it, where you've got stop valve, flow switch, and then you have a drain line coming here, which is usually 2-inch, and at this point here you've got a 15mm test valve. Okay. And you need the test valve here, which is indication of one sprinkler head not activation, and one head's in activation should activate the flow switch and then send the lamp and fire alarm panel. At this point, it's worth to note you're actually wasting water because that's going to drain. Okay. So to test that, you would open the test valve. The water would flow round and down, activate the flow switch to the fire alarm panel, and that would go to possibly alarm receiving centre, depends on the type of system. Depends on the building, the risk of the building. Generally, schools will go to alarm receiving centre. Another way to do it is installing zone checks. Not a very good picture again. However, zone check works exactly the same way, except you don't have the 15mm test line. That there, from here to here, is a test line, and what you've got is a small pump in here, which will circulate the water without discharging it to drain, and when it does that, it activates the switch, sends a fire alarm. To do that, you get the key switch, you operate it by key, it operates the pump, takes the water around the flow switch, and gives a signal. It looks something like this. Okay, so it just circulates the water around the flow switch, that paddle moves, you get a touch of the plates, you get the alarm. Okay? Now the beauty of zone checks is when you've got a large system, you can actually put an addressable system in. Now what that means is that you get an addressable loop, and you'll have many switches in that. That goes to a main control panel, and it's then connected to the fire alarm panel. Now the beauty of this is that you've got multiple ones of these. You can actually turn the switch, and it'll test every single zone check on that site. It'll then print out a report. When it prints out a report, it'll tell you what ones are healthy, what ones are not. And if you don't get any healthy, they can then call out the sprinkler contractor to do that. And save you a bit of money in maintenance, quite a bit of money in maintenance, because the last thing you want to do is have a sprinkler engineer on your site for a week testing all your zone valves. And this can be done in 20 minutes. So it's definitely worth thinking about if you do have a large site with lots of zone valves on it. Okay. Now if you go to YouTube and type in zone check addressable, you'll find a video of how it all works. Okay. I'm not going to play that, I'm sure if you go into the archives of Project Fire, they will be able to tell you exactly how they work. So I'm going to move on now to dry systems. Dry systems are permanently charged with air downstream of the dry pipe alarm valve. Okay. With the water under pressure upstream and down. So there's only be used where the wet systems cannot, i.e. permanently cold stores, whisky warehouses, anything exceeding 70 degrees, drying ovens, etc. Okay. Now, as I say, due to the time taken to release the air in the system, it takes longer for the water to get to the fire. This increases the fire area, and therefore dry systems require a larger pump and tanks to compensate for this. That's a Victaulic dry system. Looks something like that. You've also got the Tyco one, looks something like that. Okay. Now what you get in a dry system, you get a compressor, which is something looks like that one. I always prefer to use these ones because you get two compressors. One is a backup, one is a duty, and one is a backup. And what it actually does, it compresses an air vessel, and it's the air vessel it's the air vessel that tops up the system. Okay, so you've got fail safes all over the place there. The last thing you want to do is have the system trip. Okay. Get a cable coming from here, and that goes to an air maintenance device. Now the air maintenance device has got two valves. Okay, that valve is usually open. Okay, and that valve is usually shut. And that valve is usually open. And the idea is that that's your pressure relief valve. That tells you what the pressure is, and that maintains the air in the system. Now, what you can then do is you can shut this valve. When you're filling the system originally, you can shut that valve and open that valve, and that's a quick valve. Now, if you go this way, you've got the orifice. You've got an orifice union there, so there's a small hole in that which the air trickles through. If you do it that way, it does it quicker. Okay, so that's what your air maintenance device is for. That is then connected to the system, and it tops this part of the system. So as I say, downstream of the system, which is after the clapper, up here, and it keeps air in the system. You've got water charged below it. Okay. So how does that work? So it looks something like this. Okay, so you've got the yellow is air, and the blue is water. Okay. Right, your compressor sits somewhere, not in there, but anyway, your compressor there charges it with air. You get a fire, it's operating, the air's releasing, so what's going to then happen is your clapper's going to rise, allowing the water to flow through. That allows the water to flow through, expelling all the air, gets to there, and operates the system. And then, when you want to reset it, you basically drain the system, you hit the reset knob, let the clapper set down, you fill it full of air again, and then that's you back online. Okay. It's very like a wet system, it has to expel the air before the system gets water to it. That's your air system. Well, sprinkler systems aren't any use if you don't have a water supply. Okay, no water in at one end means no water out at the other end, means no sprinkler. So they can either be a town's main supply, with or without booster pumps. Pump and tanks, you get single, which is one pump, one tank. Superior, which is two pumps and one tank. Duplicate, could be two pumps or three pumps, two tanks, and they can also be fed from an inexhaustible source such as a river or canal. You can actually use elevated reservoirs, like if you've got, for instance, if you've got property at the bottom of a hill and there's a reservoir way up the top of the hill, you could actually feed your sprinklers from that. And pressure tanks. If you like, pressure tanks in a sprinkler system are basically just a big fire extinguisher. Okay. Righty. So, pre-calculated systems, what you get your installation control valve here, and this is how you determine the flows and pressures that you require at your pump for pre-calculated systems. You need to know the height difference between your sea gauge and your height at highest head. You take that height and times it by atmospheric pressure, which is 0.098. Okay. And whatever that is, you keep that to the side. That's called PS. You then get table 6. And if you look down the left-hand side, it tells you your ordinary hazard classification, which you've already worked out, and it'll tell you the requirements of your installation. It's 1100 at 1.7 plus PS, which you get from here. 1350 1.4 plus PS. That's your pre-calculated system. That's what you need here. Okay. Probably the most difficult thing you need to do in a pre-calc system, to be honest with you. Okay. Now, when you know the height of your highest head, you can then go to table 5. And down here, we'll just say, for instance, this is 13 metres. Just say, for instance. We've got ordinary hazard group 3 wet or pre-action. We're up to 13 metres high, so the height is up to including 15 metres, and that is the duties of my pump. 1350 at 2.9, 1100 at 3.2, and then my overall duty is 2250 at 1.4. That's the parameters of my pump. And that's where you get your pre-calculated pump sizes from. And then you need to work out your tank size, and again, it's very simple. You then go to table 9 in the main rules. Ordinary hazard group 3, wet or pre-action, 13 metres is there, so my tank size is 135 metres cubed. All down, in pre-action systems, all down to the height of your highest head. Okay, so just to recap on that. So PS, with 10 metres high, so 10 metres is 0.98 bar. Okay, we've got ordinary hazard group 3. Our system required there would be 1100 litres a minute at 1.7, which you get from the table, plus the 0.98, so it would be 2.68 bar. 1350 would be 1.4 plus the PS, 2.38 bar. Take that for here, there's your pump size, and there's your tank size. Very simple, very straightforward. Very simple to get our tank size from that. On a pre-action system, fully hydraulic calculated systems are a lot more difficult. Right, so back to types of water supplies. So Towns Main booster pumps. The Towns Main shall be tested to ensure it can provide 20% more than the maximum demand flow rate, i.e. 1350 plus 20%. Okay. The pressure at least half a bar measured at the pump. So to use a booster pump, you need the flow. Okay. If you don't have the flow, you can't use a booster pump. Right? And you need the 20% more as a safety factor. Right? And once you've done that, you can install a booster pump. That's an old one there, but they're all roughly the same. Okay. Towns Main has to be fed from booster pump and then come in Towns Main and bypass. Okay. There's a triple P, or you get the pressure check pump, which will work the same. They all work the same, to be honest with you. So you've got Towns Main supply coming in here, your bypass, come along your system, that comes in to your pump, you've got a jockey pump there. Your triple P and your zone pressure check system are both exactly the same. Okay. Then you're into pumps and tanks, so that's basically a single pump and a single tank. So that tank there, I think, ordinary hazard group 3, so it's 135 cubic metres per single pump. So you've got a single electric pump in there, fed from that tank, with a jockey pump to maintain the pressure. Now it's worth to note, the jockey pump is sacrificial. It's only there to maintain the pressure to stop the big pump kicking in. However, if you lose the jockey pump, there is a fire, it's the main pump that you're wanting to work, because the jockey pump won't handle what the system requires. It's this one that you need. Okay. Now, pump running signal here is a fire signal. However, if the pump kicks in without a sprinkler activation, you don't want to cause a false alarm. So you need to put in a signal from the pump and a signal from a flow switch. But I would recommend that if you have a pump activation, that it's sent off-site to an alarm receiving centre, just so that they can inform your technician or your engineer that the pumps are running, because the last thing you want to do is that to kick in on a Friday night, and then when you get there on a Monday, it's still going. because these pumps will keep going until they blow up. Especially with diesel pumps, they are known to go on fire. But if they have kicked in and they're not meant to, you really need to know about it. Okay. This here is a diesel pump house. There you go, you've got the exhaust pipe here, and that's a Franklin Hodge space saver tank. Looks something like this inside, so you've got a diesel pump here, an electric pump here. Always lag the exhaust pipe, don't want to burn empty. Okay, that's an SPP pump. You've got the panel at the back here. Then you get any high hazard, you get two diesel pumps here. Okay, two exhaust pipes. That's a GRP housing unit. Horrible things, but anyway. You've got a bit of fire-related lag in there so that it doesn't damage the GRP housing. Okay, and it can look something like that. This one here is Jobbing Island, the one we looked at. You get the GRP housing, and the pumps are situated in like this. Okay. Then we looked at elevated water supplies, and this can be a tank on stilts, like so. You've got to remember the static on that is 0.098 per 1 metre. So if you needed 2 bar, you'd need to be 20 metres up in the air. Just doesn't really work out. That's why I was saying if you're getting an elevated reservoir, it's probably best if you can use that. But then again, in 23 years, I've never seen one. It can be used. And then you also get pressure tanks, which are rarely used now, to be honest with you. Basically, it can be something like that. So as I say, if you actually picture a huge big fire extinguisher attached to your sprinkler system, that's the best way of describing it. But you can only use them in non-RAS Group 1 systems. Okay, so basically, that's that. Now, that's pretty much us. It's just an insight into some of the things that you'll see in the courses that we have. Some of the modules, which are, we've got module 15, which is the design of residential and domestic sprinklers. Now that is a 4-day course. And again, it's got a CPD of 60 hours attached to it. But over and above that, we also cover design training for commercial and industrial systems, and they're through BAFSA. And on my website you'll see links to them, so you get the basic design course, which covers this stuff in a lot more depth. It'll also tell you how to design pre-calculated systems. You've then got intermediate courses, which will then tell you how to do high-rise systems, multi-stage systems, drone systems, etc., etc. You then get the FHC design course, which will basically tell you how to full hydraulic calculate a job. And then you get commissioning and inspection course. So check out the website, have a look at it, get in contact if you have any requirements for any training on that. Okay. Well, that's me. Hopefully this little seminar is helpful, basically. And if you are looking for a CPD certificate, get in contact. Send me an email at ac@sprinktech.co.uk and I'll get in contact with you.